Hi, I'm Sophie Kawalec, and this is my Lab 2 motion of a falling object. So just to outline what I'll be going over, I'll introduce the purpose of the lab. I'll show my video on Tracker and the graph it made. I'll show my code with gravity and the graph that made. I'll show the code with gravity and drag. And then I'll combine all three graphs and compare them. And we'll answer the what if, what does it mean questions. And then we'll, in the conclusion, I'll talk about any potential errors. So the purpose of this lab is to observe the motion of an object that is dropped from rest and falls somewhat slowly. I used a covered up piece of paper. That way it actually had drag to make it slow down. I compared it with the model of just gravity and then one with just drag, and we were able to see the effects of drag and how that graph matches the observed graph best. So things to know beforehand, Newton's second law, F equals ma, we'll see that the one with just gravity, F equals the force of gravity, and then the one with gravity and drag, F net, will be the force of gravity plus the force of drag. We need to know velocity equals change in position over time, because that's what I put into my code. So now I'll share my screen to my tracker video. Awesome. So as we can see, my last point is negative 0.925. And this shows y is negative because I dropped it. There's no x graph because it's not moving left to right. Velocity is also negative because it's being dropped. Okay, now this is the code of the graph with just gravity. My ball's mass was 0.09. This is the initial position it was at that I got from Tracker, and I used the change in position over time equals velocity to find the initial velocity from Tracker. Acceleration is 9.8. This is the drag constant, and it's 0 because this one's just showing gravity. And for this one, F net equals just W. We don't have any drag yet. So this is the graph. And here we see that it ends at negative 2.22, which is drastically different from the original negative 0.925 of my video from Tracker. But the position is still negative, as is the velocity. This is code with gravity and drag. The thing that changed here is our drag constant, which is 0.31. We also changed F net, which is we added the force of drag, and we added in the equation for the force of drag, and the ball dot speed is the square root of the velocity vector. We also added an arrow to show how the force of drag is almost equal to the force of gravity and how that will create a special kind of velocity, which we'll see. Here is the graph with drag. As we see here, the ending position at negative 0.924 is almost exact as the Tracker graph. To compare all three drags, like I said, the one with drag and the video graph are the most accurate. The one with no drag goes farther and faster. And they all start together because I put in the velocity and initial position from Tracker into the codes. So what if I threw it down rather than dropping it? Terminal velocity would be different because the initial velocity isn't from rest, because you have to incorporate the force of me throwing the ball down. This graph of drag, velocity versus time, is most accurate to terminal velocity because, as we see here, the velocity is slowing down to a constant negative velocity, making that force equals 0. And like we saw with the arrows, they almost cancel out perfectly. Okay, so to conclude, in this lab, we discussed Newton's second law, including velocity and position equations. We saw F net when it's just drag and when it's, when it's just gravity and when it's gravity and drag. And potential errors is maybe the mass of my object might not be that accurate because it was difficult to weigh a crumpled up piece of paper. And that may have affected why my drag constant B was larger than expected. inserting my data into the spreadsheet was always difficult because I put it in my hand.